Welcome to our webinar, Accelerating Model Training with Gaudi Processors and Hyperparameter Optimization, brought to you by MLConf in collaboration with our sponsor SigOpt and in partnership with Habana. I'm Joe Fleischer of MLConf, and I will be your moderator. Now, during our webinar, you will learn how Habana, an Intel company and leading developer of AI processors, is collaborating with SigOpt, our sponsor, and also an Intel company, to reduce model training times while consuming fewer computational resources, according to MLPerf benchmarks. Now, before we begin, I just want to cover a few logistical details and then introduce our distinguished guest speakers. During our webinar, you'll be able to view slides, as you can see here. They will be available for download as a PDF document when this webinar is available on demand. Now, during our live webinar, we will intersperse 3 polling questions, and when we display a polling question, you are welcome to select the radio button that corresponds to your response and then submit it. Although we will set aside time toward the end of our webinar to address your questions, we do invite you to type your questions within your console, and although we will aim to answer your questions during the course of our live webinar, I do assure you that we'll plan to follow up on any topical questions we do not have the opportunity to address during this webinar. Also, at the end of our webinar, after Q&A with attendees, we will direct you to a number of links to more information about our sponsor, SigOpt, and about MLConf's conference in March, so stay tuned. What I'd like to do now is tell you about our very distinguished guest speakers. We'll first hear from Steve Stein of SigOpt. Steve has experience in marketing and product management of AI and high-performance computing hardware and software products. Also, Steve has quite a background specifically as an officer and engineer in the U.S. Air Force developing advanced technology for space systems. After we hear from Steve, we'll hear from Basem, Barakat, and Evelyn Ding of Habana. Basem Barakat is a large-scale machine learning engineer with Habana Labs. Basem leads efforts to accelerate AI workloads on Habana Gaudi and other Habana AI accelerator hardware, including collaboration with a team on MLPerf submissions. We'll be talking about that in just a bit. We'll also hear from his colleague Evelyn Ding, who is a senior machine learning engineer at Habana Labs and previously occupied the same role for Intel and focuses on data analytics, machine learning, application development, optimization, and deployment for at-scale machine learning and deep learning projects. Now, before we hear from Steve of SigOpt and then Basem and Evelyn of Habana, what I'd like to do is pose our first of 3 polling questions. So what I'm going to do now is pose our very first polling question, and that is, we would like attendees to indicate the extent to which you agree with the following statement, that your organization has optimized hyperparameters as much as it possibly can. And so what attendees are welcome to do is select the radio button that corresponds to your answer and then click on the submit button so that we are able to record your response. From top to bottom, the choices are strongly agree, agree, disagree, strongly disagree, or I don't know. Again, we invite attendees to indicate the extent to which you agree with the statement that your organization has optimized hyperparameters as much as it possibly can. We give attendees just a few more seconds to indicate whether you strongly agree, agree, disagree, strongly disagree, or I don't know. We're going to close this poll for now. At this stage, it is now my pleasure to turn the floor over to Steve Stein of SigOpt. Please give a warm welcome to him. Thank you very much.
All right, thanks, Joe. Thanks, everyone, for having us here at the MLConf webinar and to let us talk to you about SigOpt and our collaboration with Habana to be able to help them submit a new MLPerf benchmark. And so today I'm going to go over just a few topics. I'm going to start with an overview of SigOpt and how we deliver value, and then I'm going to pass it over to Basem and Evelyn to talk about their use case and specifically how they're able to improve their homegrown optimizer to submit a better MLPerf benchmark. And then we'll leave a little bit of time, of course, for Q&A and also give some information about how you can access SigOpt and Habana. So let me start with SigOpt. So modeling is messy, and it's never easy, or it's never as easy as just running one experiment or one model to get the perfect result. Modeling really does require experimentation, and SigOpt helps you design experiments the right way using our intelligent experimentation platform to give you the right results. And what intelligent experimentation means, at least what it means to us at SigOpt, is designing your experiments to ask the right questions, exploring the modeling space to help you better understand your models, and optimizing your models in a way that helps you meet your specific modeling needs. Every single use case, every single type of experiment or model that you create is different. And we want you to be able to optimize your models to the point where you get the biggest impact out of your simulations, and specifically getting the best out of each simulation run. We know that each simulation requires an immense amount of IT resources to be able to run each and every single simulation, whether that is in the HPC, high performance data analytics, or AI. So we want you to better organize, better intelligently run your experiments. And that's what SigOpt really does. And we really think of this design, explore, optimize process as a cycle. And as you explore and optimize your models, you're going to gain the insight needed to help you better design experiments and ask better questions that you didn't think of before if you didn't go through this process. And as you are starting to design better experiments, then that in turn lets you help explore the models better, look for different metrics, look for different parameters, to then better, or at least to then better optimize your models and deploy them out into the real world. And then round and round you go around this intelligent experimentation process until you found the best model, the best value of running your experiments. And that's what SigOpt really gives you. And SigOpt helps you automate all these painful tasks of modeling and going through these experiments. And we help you, automate these painful tasks so modelers can help spend their time more focused on the problem and apply their own domain expertise to the problem instead of having to fiddle around with how these experiments are run and finding the best metrics. And so, which is a few lines of code, SigOpt allows modelers to track experiments, to visualize their metrics, and execute scalable hyperparameter optimization. And this empowers modelers to create faster models, improve their productivity, and reliably improve their model performance, all the while consuming less IT resources. Because again, these models, as you're running them, they consume a lot of resources, especially as you're training deep learning models. You want to be able to optimize your IT resources and consume the least amount as you're trying to optimize your models. And we're designed to be entirely agnostic in terms of modeling framework, your task, your library, your problem. We're really designed to help fit into your modeling environment as easily as possible using a very easy to use API. And we help organize and visualize your runs and insights into a very easy to read dashboard. So you know and you can track the right experiments and the parameters and know that you're on track to find the best model that you can. And so within this design, explore, optimize framework, SigOpt really helps provide some very specific values and very specific tools to help you on your modeling journey. And what these kind of look like is under the design portion of this, we really want to help you design the right set of questions to ask, again, by helping you choose the right types of data, choose the right types of models that you want to try to run so you can design the best experiment. And under the explore part, this is where you get to choose the best metrics that you want to track. And by the way, it's not all about can you train the fastest model. Usually you want to ask the question, are you actually achieving the right business use case or business value that your organization is trying to get to? Or you're trying to set some guardrails around the metrics. You don't want it to have too slow of an inferencing. You don't want it to consume too much power. These are different types of metrics you can track, or if there's actual large scale production metrics that you want to track, such as, are we getting the right click-through rates? Are we targeting the right types of customers? Is our manufacturing process throughput fast enough? You can try to put those types of metrics into this explore bucket to make sure you're tracking the right types of metrics. And finally, with the optimizations, we provide various types of optimization methods, including the option to bring your own optimizer. And actually, with this one, here's where Habana really got a lot of value out of SigOpt, but being able to optimize their own optimizer using this bucket. Now, keep in mind, you're not going to use all these tools with every model and every experiment that you're running, as SigOpt or as Habana is going to show you, but we do provide the option to be able to track your experiments correctly, design them, and explore them, and then finally optimize them. And keep in mind that SigOpt sits a part of the larger Intel AI stack. And what the larger Intel AI software stack is really trying to do is trying to optimize AI performance and allow you to run experiments faster, allow you to get the best use case or at least the best value out of using Intel hardware. And the entire stack is kind of set up to help provide tools that specifically accelerate hardware, such as, say, new instruction sets or math libraries or new types of acceleration libraries. We also provide pipeline tools to help you run your MLOps more efficiently, specific framework optimizations such as framework or such as PyTorch and TensorFlow to be able to get the most use out of those actual frameworks themselves. And then finally, the ability to actually get the most out of each modeling run or design experiments in the right way, and that's where SigOpt lives. So with that, I'm going to pass it over to Habana, who's going to give you a quick overview of their use case of being able to optimize or use hyperparameter optimization engine inside of SigOpt to get a better MLPerf training result.
Thank you, Steve. We do want to actually pose our second of 3 polling questions, and then we will hear from our distinguished guests from Habana. And our second of 3 polling questions asks attendees to indicate the following. Specifically, we want attendees to indicate the extent to which you agree with the statement that minimizing training times without requiring more computational resources is your organization's top challenge when optimizing hyperparameters. And what attendees are welcome to do is, with our first polling question, is select the radio button that corresponds to your answer and then indicate your choice. What we're going to do is give attendees sufficient time to respond, and then we look forward to hearing from Basem and Evelyn of Habana to share their perspective. We'll give attendees just a few more seconds to respond, and just to reiterate, we want attendees to indicate the extent to which you agree with the statement that minimizing training times without requiring more computational resources is your organization's top challenge when optimizing hyperparameters. What I'm going to do is close our poll, and it is now my pleasure to turn the floor over to Basem and Evelyn of Habana. Please give a warm welcome to them. Thank you very much.
Hello. My name is Basem Barakat. I'm a scale-out performance engineer with the Habana lab. Today, I would like to share with you the overview of the optimization work the Habana team done in the context of our most recent MLPerf training submission. This is namely for BERT and ResNet 50. The work here we're showing is we're talking the ResNet 50 BERT, ResNet 50 work, hyperparameter optimization for ResNet 50, but we're also done the same thing for BERT. I have the link here. You could see the results if you wish. And I will be talking about the constraint of the MLPerf training benchmarks. So the method, very general, like I mentioned, it applies to many workloads. Here we'll be discussing the ResNet 50. So also I would like to mention there's so many ways to optimize a workload. Obviously, you could optimize the model itself. You could optimize, but this is a benchmark. So we're very much constrained in what we could optimize. So we chose to optimize the hyperparameters, which allowed under certain constraint from the MLPerf rules, which we will discuss. So the whole idea is, of course, if we could get the same model to run on the same hardware, and in this case is Habana Gaudi's. These are distributed accelerated networks. So under the same condition, the same distributed network, you could just make it run faster in the way it could converge faster by just tweaking the hyperparameters. So that will gain you a performance leg. As all of you knows, training is very expensive. So that's why people use accelerated networks, and they use distributed computing models to speed up the computations. And here we're just adding the hyperparameter optimizations. Of course, speed up here is when the model converge. So you will have the desired accuracy for your training, for your evaluation data set. So key information I would like to mention and highlight here. So obviously, like everybody else, we start with the known hyperparameter values, and we start our optimization work. Now, computations are plenty, and we have a lot of them, but they're shared computations. So we have DevOps, we have a development team, we have QA team. So we share the clusters with so many other teams. So there is a premium on the computation, although it's plenty. So it's not infinite, it's not free. So we have to be mindful how we utilize our compute node. So obviously, we would like to use the least amount of computation node in the shortest time. So that's I mean, it sounds trivial, but we just want to emphasize that part. So here I would like to mention what we're optimizing. I mentioned it quickly, but so like it was mentioned in the introduction by Steve, you could optimize the model themselves, but this is a benchmark where we're comparing our hardware and our compute infrastructure to others. So we can't, the models is fixed. You can optimize it. But we could optimize the optimizer. So here we're optimizing the loss functions. And the loss function is the large functions. And I included the references, the paper references, because you could go and learn more about this. I will discuss the actual hyperparameters in the next few slides. But basically, there are two papers you could start with. Is the one for ResNet is what's called the large optimizer, and the ones for BERT is the LAMP optimizer. They're very similar. And for completeness, I included what the large algorithm looks like. They're just a capture from these two papers, so you could have an idea about what these values, which I'm going to be discussing, are. So we started with a homegrown search. It's a grid search, but it's really we're doing the explore and the exploit part manually. So it's a manual, so it's not like systematic. It's very expensive to do grid searches or any hyperparameter search. So let me first discuss what hyperparameters we're doing. So obviously in the training, we have the number of training epoch, how long you want to train. And this is an integer, in positive integers. And the number of warm-up epoch, if you go back to the paper, you will find Lars like to for the weight distribution is to warm up it does a schedule optimization. So the schedule is ramped up to the base learning rate, which is the third parameter we're optimizing over several epochs, and then it decayed throughout the training process. So we have that. It's another integer basically. And then you will have the base learning rate, and that's the maximum learning rate the schedule will start is, and then the weight decay, and the weight decay is your typical weight decay float, and the MLPerf have a constraint on the values of this weight decay, and basically it has to be 0.0001 time to the n, where n any integer, and so that's basically here, and we chose our metric to, obviously we have to have evaluation accuracy. So using the evaluation data set, you have to have an accuracy larger than 0.759, which is the universal plateau for the ResNet 50 in this case for the accuracy, and the converge epoch. So the converge epoch, it's really the same as the training epoch, but is the training epoch at which this accuracy is reached. So we call this as the converge epoch. So this is really weird. We have the metric is the same as parameters, but with the qualified condition. So this is, so basically we would like to use the least amount of epochs in training these data sets. So the manual search, it starts by just a typical nested loop where we have our epochs, the warm-up epochs, the base learning rate, and weight decay, and we have a list of values. So these are the list of value. We start with the exploration side, and then we see how's the data trending, and then we do run workload with these values, and we get the metrics back, and we increment our run number. So and then, which Evelyn's going to discuss, and we're going to discuss, we have an evaluation process to see how those sets of parameters doing, and to see how to explore which area we need to explore next. So with this method, we're able to reach a very decent. So we lowered our conversion epochs by 28% in compared to what we started with, and that's linearly correspond to lowering the training time for a given computational networks. So here I included some data, how many runs we had to do. So we have a Kubernetes runs. We included them here. We have a bare metal runs, and basically 85,000 runs we ran. And with that, we reduced it to about 28%. So then we said, okay, is this the best we could do? And obviously, we were very happy what we've done manually, and we decided to unleash an optimizer on these hyperparameters. These surfaces are very complicated, and basically, we followed the trend in our manual search, but we don't know if we left anything on the table. So we decided to go ahead and use an optimizer, and we were having several options to select from, but we decided to go with SigOpt because of the following. So we have a lot of code deployed in our infrastructure, and we just didn't want anything else to install. So SigOpt was very quickly to start with. It's a cloud-based API. It's very easy to integrate with your launch scripts, and so that's what I started with. And then the major part, which I like, is supporting the parallel evaluation. So they could give you suggestions for several runs at the same time. So because we're doing training and distributed networking, so these runs, it takes a long time, and running them sequentials, that mean it's forever. And so if you could run several runs together, that will help a lot. And of course, once we started using it, we got very quick response back from the support if we stuck here. And basically, of course, most people give you manual to read, but if somebody at support could nudge you and tell you, okay, it's in the documentation, that's the section you need to look at, or so it helps a lot make you move, and that's what happens. For our deployment, we had a cloud-based or a cluster-based here on the top right, and that deployment, it's the same for SigOpt and manuals. And we sit here at the launcher terminal, so that's us sitting, that icon. We sit at the launcher terminal, and that launcher terminal, basically we launch a script, and then we have a script to get the result back from these jobs. So we could run 64 Gaudi's runs, or 8 Gaudi runs, or 128 Gaudi runs. So those we could launch and we could get the results. Now, in the case of the SigOpt, so we will have a connection to another cloud where the SigOpt code is here on the bottom left. And here, basically, we get suggestions from the SigOpt optimizer and tell us, okay, try these values. And then when we get the result, we relay them back. We could relay them back to the SigOpt, and they come back with new suggestions. So basically, that's the experiment cycle. It's so simple. You will have a terminal with an operator. We launch the experiment through a launcher script, and then we get the result, and we relay them back to SigOpt. Here, I will turn to Evelyn to walk you through the actual code.
On this slide, we develop a process flow chart to show our software execution plan for us to how we use the SigOpt to help with our hyperparameter optimization work. So we can see from the left-hand side, we started the SigOpt by initialize. The first step is by initializing a few key parameters as below. We need to initialize the hyperparameter initial boundaries. We need to define the evaluator matrix threshold. And then the next one is the experiment budget. So for our case, we normally define the 100 as the budget for each of the experiment. And then the next parameter is the computation resources. So this depends on the availability of the number of accelerator we plan to use. The key parameters, which is the parallel run budget. So for example, if we define the parallel, the bandwidth with 2, then if we have the 64 accelerator available, so we can run 2 set of the 32 accelerator at each time, which can be significantly help us to speed up the experiment. Then we are going to define, create, and configure the experiment. And from this point, we started our main execution loop. So the main execution plan has been divided into the 2 major loops. The one in the middle with the dash dot dash line, that's our inner loop. And the bigger line, the dash line, which is the outside, which is the wider range, that's our outer loop. So the inner loop is defined as a user and a SigOpt interface. So for when we run our experiment, for each loop iteration, we fetch the hyperparameter suggestion from the SigOpt. Then we test all these parameters by training our workload on our cluster. Then we evaluate it based on the metrics, if it is past the accuracy or not, and how fast it is running based on the converge epochs. And this inner loop has been iterated for a number of times until we reach to the maximum defined budget. So during the whole the searching process, we can tracking the progress on the SigOpt dashboard. Then after we finish iterate the one set of the experiment, we get out, we started our outer loop. So the first condition is we define as a condition with the converge epochs new from the latest iteration loop compared with the converge epochs old. If the differences between the new converge epochs and the old converge epochs more than 1%, we will continue this outer loop to the next step. We go up, and we will transfer the we will replace the new converge epochs number with the old converge epochs number. Then we are going to start it to evaluate all these boundaries by using the step is evaluator blocks, which is we use the k-mean cluster method to further evaluate the SigOpt boundary. Then once we adjusted the boundary to once we adjusted the boundary, and the new SigOpt boundary will be defined and prepared for our next experiment. And this outer loop will be iterated for a number of times until we reach to the condition that the new converge epoch will not change anymore, which means that the differences between the current loop and with the previous loop less than 1%. Then we get out of this outer loop. Then we save all the data point, and we have a list of the latest recommendation, the hyperparameters that's ready for us to use. Then we stop the SigOpt. In this slide and the next slide, I'm going to talk about a little bit more detail how we build up the evaluator blocks by using the k-mean unsupervised machine learning algorithm. So on the top left corner on that chart, that's the parallel coordinates that we get after each of the experiment. So we collect the data with all the hyperparameters and with the metrics. Then we will pick up all the data point which only pass the accuracy threshold. And also, in the meantime, we also selected the top 75% of the data point with the smallest converge epochs. So we collect all this good data set. We are going to do the cluster, split into the different cluster. Then we our principle, the baseline is to keep at least 10 observation in each of the cluster. Then we can easily see from the bottom right corner that if all the data point based on the distribution, the data point will be distributed into the split into the different cluster. Then we pick up the best cluster based on the criteria that has the minimum runtime mean in that cluster. And from the left bottom chart, you can also easily see that from the box the plot, we can find out which the cluster has the minimum the runtime mean. Then the one highlighted in the light blue is the best cluster we select as an example. So on this slide, I'm going to continue talking about how we build up the evaluator block. So on the top left corner chart, once we pick up the best cluster, we are going to transfer the boundary of all the data point and which one the highlighted in the red dot circle, we're going to translate to the right, which is highlighted in the range in the search space defined by the red square bracket. And we use this best cluster boundary to, and also the widest the black square bracket, which is the absolute hyperparameter range. So we will adjust the SigOpt range between the black and the red bracket. So the SigOpt suggested range is the one highlighted in the light blue. And so we follow the path on the bottom left corner, the logic, we define the logic flow chart. And it is follow the two paths. For example, on the red path, we are going to compare the SigOpt upper boundary, the SigOpt recommended upper boundary with our best cluster upper boundary. If two upper boundary very close to each other, let's say, for example, 30%, if they're too close to each other, then we will move the SigOpt upper boundary towards to the right, close to the absolute hyperparameter boundary. That's going to be help us to improve the exploration of the global search for all the search space. And on the logic when we adjusted the lower boundary. For example, if we compare the SigOpt lower boundary with the best cluster lower boundary, if it is very far away from each other, we will move the SigOpt lower boundary towards to the best cluster lower boundary. So we will move the lower boundary towards to the right. So that's going to help on the exploitation of the search for the local optimum search. So by using this this method, we further narrow down the space, the SigOpt, the recommended the boundary. That's prepared for our next experiment run. So from the user perspective, we really like the feature of the SigOpt and provided, because that's give the flexibility for the user to build up their own optimization method on top of the SigOpt optimization. So that's going to be fit for the different scenario. Okay, so right now I'm going to hand over the presentation back to Basem, and he is going to give some comparison of the SigOpt search and our the manual search, and also going to provide a few conclusion at the end. Thank you.
Thank you, Evelyn. First, I would like to talk a few things we liked about SigOpt. We love the dashboard of SigOpt. So we could see the parallel plots of the hyperparameters, how they're progressing through the experiments, through the runs within each experiment, and how they correlating, inversely correlating, or linearly correlating with each other. So that's a very good insight. And also we like to see how the run's going. And also we would like to see how the metrics, in our case, the converge, the training converge, and also the training epoch converge, or what we call the converge epoch, correlate with the rest of the hyperparameters. So very nice visualizations, and that's what we like. So here, just to list some results which Evelyn talked about, inner loop and outer loop. So in the inner loop, again, I just remind you, what we do in the inner loop is we run one SigOpt experiment, and in each experiment there is 100. In our case, it's 100 runs, but it could be any number you want to set. Here, so after 200 runs, we immediately got 2% improvement compared to our already optimized manual search. And with another outer loop, this is the 300 run, we got a 6% improvement. Okay, and we ran another experiment, another 100 run, and we got 6%. We didn't get any improvement, and hence we stopped. So basically, we ran all this on Kubernetes, and so with 20,000 more runs, we got 6% improvement, and we thought that's very good. So let me go ahead and compare here. So the conclusion here is, you want the Bayesian optimizer, which is SigOpt give you, versus the manual grid search. We wish we started with that in the beginning, and for anything next, we will just hit it with SigOpt right away. And it's 6% on top of already optimized workload. It's very good, and the computation results we feel, though here we're not comparing apple to apple. Remember, I'm just telling you the story how we did how we did the work. We started with a manual search. We spent roughly 85,000 hours of compute on that, and then we did SigOpt, and with 20,000 hours of compute, we got a 6% more. So we got 28% from non-optimized. So obviously, we feel SigOpt it's harder to optimize things already optimized, and for that, we feel SigOpt it's probably the way to go. Though this is not a apple to apple comparison. I think with that, I will turn the presentation to Joe.
Thank you very much, Basem and Evelyn. What we're going to do now, before we address some great questions from attendees, is pose our third of 3 polling questions. We want to find out from attendees when you plan to implement alternatives to traditional search methods when optimizing hyperparameters. And what you're welcome to do is select the radio button that corresponds to your answer. And from top to bottom, the choices are: my organization is already doing so, within fewer than 3 months, within at least 3 and fewer than 6 months, within at least 6 months, my organization has no plans to do so, or I don't know. So please select the radio button that corresponds to your answer. After we've covered this poll, this third of 3 polling questions, we're going to address some great questions from attendees, and we're really looking forward to addressing these questions and hearing perspectives from Basem and Evelyn of Habana and Steve of SigOpt. Again, we want attendees to indicate when your organization intends to implement alternatives to traditional search methods when optimizing hyperparameters. We want to now address some great questions from attendees, and that's exactly what we're going to do. Starting with Basem, you've shared the example of ResNet 50 being images. The attendee is asking, what other types of neural networks or models do you intend to evaluate with regard to hyperparameter optimization?
Well, definitely you could evaluate, you could optimize the model themselves, any model you want, like Steve mentioned. But here we're constrained because we were working in the context of MLPerf submissions, so we cannot optimize those models. They're fixed. Everybody has to run the same model. But we could really tune the loss function. And what we did, in addition to ResNet 50, we did BERT. Okay, and it's exactly the same mechanism. Of course, almost the same hyperparameters, slightly different hyperparameters, but it's basically the same methodology. And so we did BERT, and we will intend to do a few others as we move on. In addition to models, you could also optimize deployment. You could optimize the IT infrastructure. I mean, this is too much. Of course, we're not MLOps or SysOpt, but you could try to do these things. So there's basically many other places you could apply these optimization techniques to optimize your network and your models, and ultimately, in my case, is the performance of your compute systems.
Thank you, Basem. And before we hear other perspectives, Steve, I'd like to hear your thoughts. In terms of this question, what are your thoughts, just in given this question and given Basem's response?
Mm-hmm. Yeah, and he's right. And keep in mind, SigOpt is meant to help you with any type of model that you're trying to optimize, and that includes high performance computing simulations to high performance data analytics. So what we're trying to give you is this ability to try to figure out where to go next with your experiments. Like, you ran one iteration, what do you do next? How do you change the parameters to be able to give you a better results, or whatever kind of metric you're trying to track? And so we're pretty agnostic in terms of what type of model, what type of framework you're trying to optimize. We're trying to give you the tools and the platform, the intelligent experimentation platform, to do so. That's really what we're trying to give you the tool set to do. Now, keep in mind, we're not going to do everything for you. We're not going to allow you just to input your model and your metrics, and then we go in the background and we do everything for you and spit out the best answer. What we allow you to do is give you the platform to do so. So we give you the visualizations, the dashboard that gives you all the different types of ways to look at which parameters are most important, as well as giving you the outputs of how your model metric is improving over time. And most importantly, we're allowing you to give you the best, most efficient path to your best value. What that means is, again, running the least amount of simulations to be able to give you the best results, versus kind of ad hoc picking which ones, or doing a manual search to figure out how you can get the best results. And again, we do this for any type of model, and we're including more and more framework integrations inside of this as well. So we just introduced an XGBoost integration into the SigOpt to make sure that framework is more optimized as you're doing your runs, and we're going to be including more and more frameworks and better optimizations into the future. But we're more of a platform, a tool set to allow you to be more productive as you're creating your models. And we're pretty agnostic as far as which type of models, which type of frameworks, what type of data sets you want to use. You bring that to the table, we'll help you optimize it.
Thank you very much, Steve and Basem. Now, Evelyn, an attendee wanted to hear your perspective as well. In other words, the process that you outlined to the extent. So an attendee has a two-part question for you, Evelyn. The first part I'll pose first, and that is to what extent is the process that you've described applicable to other types of models? That's the first of two-part question, Evelyn.
Okay, yeah. I think the evaluator blocks that what we developed to help to define like the SigOpt boundary, I think that's applicable to any type of the workload, because the main concept is to analyze a set of the good data point, which could those data point could generated from any type of the workload, the deep learning model. So the concept is to find based on the distribution, and we try to narrow down the whole search space into a specific a different of the combination, and to narrow down the search space, which is kind of just to speed up the search space. So yeah, I think the concept is kind of applicable to any of the workload. Plus, I think we use the k-mean cluster the method. So the way we keep, because there are so many the different option of the algorithm on the clustering, the unsupervised clustering, like the fuzzy c-mean cluster. There are a bunch of others. So we keep the k-mean the most basic one, because we do not want to overtune all the data point. So we just trying to split into like every 10 or 15 into the different cluster. We do not want to be overfitting the data point. So we keep the simplest version as of right now. But in future, yeah. So if the user interested to try all the different type of the cluster and the algorithm, I think yeah, it is definitely worth of doing that exploration.
And speaking of future plans, an attendee indicated that the attendee thought there was reference to correlation analysis in connection with the evaluator block. Evelyn and Basem, and yeah, I'd love to hear your thoughts on behalf of the attendee. Are you able to elaborate further on correlation analysis as it relates to the evaluator block, perhaps starting with Evelyn and then Basem?
Okay, yes, so on the correlation, the relationship analysis, that's definitely some additional step that can help us to make a better initialize decision of how we define the SigOpt boundary. That we can kind of, we have already tried to do the correlation between the hyperparameters and with the metrics, and to ranking all the hyperparameters with the one like based on the most impact to the metrics, and we can give a wider range search on the hyperparameters with higher ranking, and with the narrow search space on the lower the ranking. But I think we compare. This is we do our analysis on the SigOpt. They provided a feature automatically on their dashboard. They use the extra tree regressor and to build the model and to ranking the importance of the features on the hyperparameters. This is kind of equivalent to our correlation analysis. So the main concept is just trying to define the boundary and the more narrow down the search space into the more target area. That's going to be save a lot of the computational resources for us to make the final suggestion decision. So yes, we can. We will try the correlation analysis. Plus, in the meantime, we are going to use the SigOpt, the feature importance, the ranking chart as well. Yeah.
Well, thank you very much, Evelyn. And actually, before we hear Basem's thoughts, Steve, did you want to jump in and offer any thoughts on this question?
No. I think she hit it just the way we like it to be said, and showing some of the main things that we provide, which is some of the ways to to rank and be able to visualize and be able to know what you're trying to look for. But yeah, that's Evelyn said it great.
Absolutely, yeah, I agree. And Basem, what would you add?
Yeah, so I mentioned during this during the presentation, very quickly, that's what we love about SigOpt is the dashboard, and the dashboard in the analysis section, it shows the parameters importance as related to the metrics. So that's very nice, and also it shows the parallel plots, which tells you visually what the correlation, so you can see it in the parallel plot. But what we would like to do is automate this, because we want to press a button and have this runs and we do something else, and then so we don't want to babysit the things as running. So it's nice to monitor it and see how it's progressing. So we would like to add those correlation analysis to the evaluator in the future updates on this. So you could it's already doing some of that, like Evelyn mentioned, by adjusting the SigOpt search space on the fly. But we would like to get this information spelled out in English, so people get the insight with each run, how things trending. And yeah, and right now you can see it visually, but it would be nice to come out from the tools itself. Thanks.
Thank you very much, Basem and Evelyn and Steve. I think one quick question from an attendee before we address some remaining items, and that is just quickly, starting, perhaps we'll start with you, Basem, and then Evelyn, and then Steve. What would you say is the most important lesson learned from your experience amid your efforts to improve upon results of traditional search methods when optimizing hyperparameters, starting with Basem, then Evelyn, then Steve?
Yeah, so the optimization is very expensive, and I understand why most people don't do it, because it's a compute resources, mainly manpower. You have to babysit these things and look at them, and the result uncertain. So it's a risk. You, after spending so many days or weeks in basically coming up not much there. So using an optimizer, so we started manually and we locked out, I will say, and then by using the optimizer tools, basically using algorithms and using math, really help you in speeding up your performance. So obviously we were working on key infrastructure. Using accelerators, using network, using high-speed networking, but a simple loss functions optimization, it help you save so much of your compute resources. So it's worth investing in it, but you have to use the right tools. And moving forward, we have this as a standard practice in our workflow for optimizing models and deep neural network performance using the hyperparameter optimization on them.
Excellent. Thank you, Basem. And then briefly, Evelyn, and then Steve. What would you say is the most important lesson learned?
I would say that the most important lesson learned is like we need to define the boundary, the initial boundary for the SigOpt to optimize very carefully. That's because if we kind of starting with a random the search space for all the hyperparameters, it's just wasting a lot of time, and it could be just result in the performance not converge at the certain area that we expected to be kind of to be as fast as what we expected. So I think define the initial boundary is very important. Plus, there are several the requirements from the MLPerf that there are some restriction on the constraint of the hyperparameter that we need to be very carefully review all their rules on each of the hyperparameters that to follow all the constraint. For example, for our BERT, the workload, and for one of the hyperparameters, there is some constraint that it can be only performed in a certain the range based on the global batch size. But at the very beginning, we kind of search a wider range, which does not exactly follow the constraint from the MLPerf. So which kind of wasting some computational resources and the time from us. So yeah, I mean this is, I think, the something we lesson learned in my mind.
Yeah, the biggest lesson I learned, I'm going to follow up from Basem's comment about how each experiment is incredibly computationally intensive. And knowing what to do next is a very tough question to answer, and I think that's what I'm starting to learn throughout this entire process of helping folks figure out what to do next in their experiments. And it's not easy, and that's where I feel like SigOpt really helps a lot, or provides a lot of value, is knowing what to do next in your experiments and getting to the best answer faster by being able to figure out what is the best value you're going to get to by not having to do a bunch of random compute runs and find the best answer that way. Because a lot of attention these days is figuring out how to make each individual run faster by getting better hardware, better software, better instruction sets to make that individual run faster. But I don't think we ask the question enough about how can we do less runs. And I think that's what SigOpt really provides the answer to, is to figure out how can you do less runs to get to a better answer rather than make each individual run faster, if that makes sense. So that's been my biggest lesson learned over this entire experience.
Thank you very much, Steve and Basem and Evelyn. Before we wrap up, I've shared a link to sign up for SigOpt for free forever. Also want to direct you to another link. This is a link to SigOpt itself, and then also what I want to do, and you can click here to learn more about SigOpt. Also want to let you know that you'll have the opportunity to get a discount, specifically 20% off an already existing early bird ticket to MLConf NYC on March 31st, 2022. Click on the button below to receive a 20% discount off an early bird discount to MLConf NYC on March 31st, 2022. And then finally, do want to ask attendees to complete a feedback survey. Once again, want to extend my appreciation to our distinguished guests, Steve of SigOpt, as well as Basem and Evelyn of Habana. We thank you again for joining our webinar, Accelerating Model Training with Habana, Gaudi Processors, and SigOpt Hyperparameter Optimization, brought to you by MLConf in collaboration with our sponsor SigOpt and in partnership with Habana. We thank you for your time, and we hope you enjoy the rest of your day.